नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। अगर आपने हमारा चैनल सब्सक्राइब नहीं किया है तो प्लीज उसको सब्सक्राइब कर लीजिए और वीडियो देखने के बाद अगर आपको पसंद आता है तो प्लीज उसको लाइक कीजिए। तो आज हम जेई मेंस रिवीजन का आज चौथा दिन है और आज हम डिस्कस करने जा रहे हैं रियल गैस के बारे में। So let us start with real gas. So about real gas, we have already made two videos regarding intermolecular forces. So I'm not going in very detail in intermolecular forces because there are separate videos regarding them, and I will share those videos or put a link of those videos along with this. So let us start. When we are discussing about ideal gas, there are certain assumptions in kinetic theory of ideal gas, like gas particles have negligible volume. There is no interactive forces between ideal gas particles. But these assumptions are not valid in case of real gas. In case of real gas, we have to consider the volume of real gas molecule. So two assumptions of kinetic theory of ideal gas is not valid in case of real gas. Volume of real gas molecules is not negligible with respect to volume of container. This is the first one. And the second one is there is interactive forces between real gas molecule. We know that in real gas there are both type of interactive forces, attractive as well as repulsive. Under certain conditions, attractive intermolecular forces will dominate. Under certain conditions, repulsive forces will dominate. So about different type of interactive forces and its variation with distance, separation distance we are discussing. So the first one is dipole-dipole interaction. In case of dipole-dipole interaction, there are two types of molecule. One molecule is stationary and the other is rotatory. So stationary means if we take solid substance like ice, in that there is hydrogen bonding, because of that the molecule is stationary in that. So in that case, interactive forces is directly proportional to 1 upon r to the power 3. Then in dipole-dipole interactions, when the molecules is rotatory, like sulfur dioxide is polar molecule, or H2S is polar molecule. So there is dipole-dipole interaction and the molecules can rotate. Their interactive forces is directly proportional to 1 upon r to the power 6. In dipole-induced dipole interactions, interaction between Cl2 gas and HCl gas. So HCl is dipole and Cl2 is induced dipole. In these type of interactions, the interaction energy is directly proportional to 1 upon r to the power 6. And induced dipole forces, London forces, dispersion forces, or London dispersion forces, which act between non-polar molecules like hydrogen molecule, chlorine molecule, bromine molecule, or fluorine molecule. So induced dipole force of attraction, interaction energy is directly proportional to 1 upon r to the power 6. So except this stationary molecule, in all intermolecular forces, interaction energy is directly proportional to 1 upon r to the power 6, except where the molecule is stationary. Now, if there is an interaction between ion and dipole, it is not intermolecular. I have discussed this. So ion-ion interaction, when we write that what is the potential energy between a positive and negative charge, we use the formula that potential energy is equal to 1 upon 4 pi epsilon naught q1 q2 upon r. So there interaction energy is directly proportional to 1 upon r. And in case of ion-ion interactive forces, they are long range forces. They are valid at long distance, while when discussing about intermolecular forces, they are short range forces. They are valid in short range of distance, about 500 picometer only they are going to valid. So when we are discussing about intermolecular repulsion, because these are van der Waals forces are always attractive. So some of the students get confused that van der Waals gas and van der Waals forces are always attractive means van der Waals gas has only force of attraction. That thinking is wrong, right? The interactive forces which is attractive is known as van der Waals forces. Between real gas molecules, both attractive as well as repulsive forces are there. So the repulsive forces are active when the molecules are very nearer to each other, like when the distance between them is equal to their diameter, means they are touching each other, then in that case repulsive forces will dominate, and the interactive energy in repulsive forces is directly proportional to 1 upon r to the power 12. 1 upon r to the power 12. So when we are saying about interactive forces, think about both attractive as well as repulsive, and the sum of that will decide the net interaction energy. So this is a graph of potential energy versus separation distance between two molecules. We are discussing about two molecules. When these molecules are very far apart, when the distance between them, separation distance is large, then there is no interactive forces. If there is no interactive forces, potential energy will be zero. We are discussing about this reason. When the molecules are separated by a large distance. Now when the molecules are coming nearer to each other, the force of attraction is increasing. So till here the force of attraction is increasing. At this bottom point there is no force of interaction, and then again from this minima point, if we further move to the left, then repulsive forces are dominating, and here the potential energy of the system is equal to zero. So on this graph, if we draw tangent at different points, and we know that force is equal to minus times of change in potential energy with respect to separation distance. So the interactive forces is attractive or repulsive, we can find out. If we are getting negative sign, means interactive forces is attractive. If we are getting positive sign, means interactive forces are repulsive. So from this, if we say that this is a point where we are drawing the tangent, so on this curve, if I name that this is point A, this is point B, and this is point C. So the slope of tangent at point A is negative. So change in potential energy with respect to separation distance is negative, minus is there. So force will be positive. Positive means there is force of repulsion. So at point A is telling that when we are increasing, when we are changing the distance, right here repulsive forces are dominating. Same way when we are discussing at point C, the slope of this tangent at point C is positive. It means that force is negative, means there is force of attraction between the molecules. And at point B, if we draw the tangent, the slope of tangent is equal to zero, means du upon dr is equal to zero, means there is no interactive forces between real gas molecules, right? So here the force will be zero. This sigma in this graph, sigma is the distance from origin, right? So this is the distance between, this is the separation distance from here to here. At this separation distance, the potential energy between two molecules is equal to zero, and this height is known as well depth, and this well depth is telling about the type of force of interaction, that the force of attraction is strong or the force of attraction is weak. If this well depth is more, it means that the real gas molecule have more force of attraction. Smaller the well depth means the force of attraction between the real gas molecule will be less. So well depth is also important in this graph. So this is about variation of potential energy with separation distance. Now we know that there are many type of real gas. One of them is van der Waals real gas. So many type of real gas equations are there, but one of them is van der Waals real gas. So we are going to discuss about van der Waals real gas, because apart from van der Waals real gas, there is Di-Teresi real gas, there is Berthelot real gas. So van der Waals real gas equation is P plus N square A upon V square V minus NB is equal to nRT. In this equation, pressure P is pressure of real gas, V is volume of real gas, or we can say V is volume of container. For ideal and real, volume of container is volume of the gas. But what is the difference in case of ideal gas? Volume of container is the free volume, because the volume of gas molecule is negligible. But in case of real gas, we cannot neglect the volume of real gas molecules with respect to volume of container. And because of that, the free volume in case of real gas is different. We are going to discuss about free volume. N is the number of moles of real gas. R is universal gas constant. T is temperature of real gas in Kelvin, or temperature of the container. So temperature of gas is temperature of container. A and B are van der Waals real gas constant. And the value of van der Waals real gas constant is independent of temperature and pressure. We have to understand that Why the value of A and B is independent of temperature and pressure? Because the value of A and B is derived from critical constants. What is critical constant of a gas or of a substance? Suppose if I'm talking about water, this is triple point where solid, liquid and gaseous or vapor state of the substance are in equilibrium. If we move along this curve, at this point, this is critical point. So critical point is a point. We cannot change the value of critical point for a substance. For water, the value of critical point is fixed. Means pressure corresponding to critical point, temperature corresponding to critical point, and volume critical corresponding to critical point is fixed. So in case of van der Waals real gas, when we derive critical pressure, we are getting that critical pressure is equal to 1/27 A upon B square. Critical temperature is 8/27 A upon BR, and critical volume is equal to VC, which is equal to 3 times of B. 3 times of B. So here we are not deriving this critical points. We are discussing that PC, VC and TC is experimentally determined. For a gas, it is not going to change. The value of A and B is derived from PC and VC. We avoid the calculating the value of B from VC because there is no instrument to measure the volume. There are instruments to measure the pressure and temperature, but there is no instrument to measure the volume. So when we calculate, there may be human error chances. So we avoid to calculate the value of B with respect to critical volume. So the value of A and B is obtained with the help of critical pressure and critical temperature, because there are instruments to measure temperature, there are instruments to measure pressure. So it's important that since critical point is not changed, and for a gas, a value of A and B is obtained from critical pressure and critical temperature, therefore we can say that A and B is independent of temperature and pressure for a van der Waals real gas. Different gases has different critical point, so the value of A and B is different for different gases, but the value of A and B is independent of temperature and pressure of the gas. So this point is important. In JEE Advanced, they have asked this question that what is about A and B, what is true about A and B. Now next point, unit of B and unit of A. We are going to discuss about the meaning of A and B, but first we are discussing about what is the unit of A and what is the unit of B. So when we are writing V minus NB, we can add or subtract volume from volume, right? So if V is volume, NB has the unit of volume, from there we can say that the unit of B is equal to liter per mole. So unit of B is equal to liter per mole. Same way, when we are discussing about pressure correction, P plus N square A upon V square, we can add pressure in pressure, right? So in this is pressure of real gas and this is pressure correction. So its unit is equal to that of pressure. So from there, if I calculate what is the unit of A, so pressure is in atm, then atm into liter square per mole square. So unit of A is equal to atm liter square per mole square. Now we are going to discuss about volume correction, right? So suppose this is a container whose volume is V. V is the volume of the container, and in this container a real gas is there. So if I collect all the real gas molecule, these molecules will occupy some volume. So this portion of the container is the free volume. So when we are discussing about free volume is equal to volume of container minus volume occupied by real gas molecules. So in case of bimolecular collision in gaseous state kinetic theory of gas, we study that bimolecular collision, when two molecules are colliding together. So due to random motion, if this is the molecule, the other molecule can come and collide with this molecule from any direction. Suppose at a time this other molecule is coming from this direction. It means that in this spherical region there is no center of the third molecule. If the center of the third molecule will come, then it is not a bimolecular collision. So in gaseous state, we are assuming that only bimolecular collisions are taking place. So in that case, this big sphere volume is occupied by two molecules. So we are saying volume occupied by two molecules is equal to 4 by 3 pi. Radius of this big sphere is equal to 2r, so 2r whole cube. From there we can calculate that volume occupied by two molecules is 8 times their own volume. So volume occupied by one molecule is 4 times their own volume. So B is known as co-volume. Co-volume is very logical. Co means together. So together they are occupying this volume, or we can say excluded volume. In this volume, no third molecule can enter. So that's why its name is excluded volume. So co-volume, excluded volume is denoted by B, which is equal to volume occupied by 1 mole of real gas molecule. And we know that B is equal to 4 into volume of one molecule into Avogadro number. So student, remember that B represents, because they remember V minus NB, N is equal to 1. So B is the volume of real gas molecule corresponding to 1 mole. That is very logical to remember, but they forget this 4 factor. So what they will write that Avogadro number into 4 by 3 pi r cube, they forget about this factor 4. So keep in mind, this is a common error done by the student in exam, and I have told you that what is the logic behind that. Now if we calculate what is the value of NB, N is the number of moles, so volume occupied by N mole of real gas molecule. So from here we can say that V is the volume of container and NB is the volume occupied by N moles of real gas molecule. So in order to determine the free volume, if I subtract the volume of real gas molecule from volume of container, will get the free volume. So we are writing that free volume is equal to V minus NB. And before discussing about pressure correction, I want to say here that B is related with size, because we are saying B is equal to 4 into 4 by 3 pi r cube into Avogadro number. So 4 by 3 pi r cube, R is related with size of gas molecule, real gas molecule. So B is related with size of gas molecule, as well as when we are saying that when we are keeping these molecules together, the distance between the molecules is of the order of their diameter. When the molecules is at a distance of diameter, repulsive forces are dominating. So this has relation with repulsion also. We're going to discuss that how it is going to affect the pressure. NB factor, how it is going to change the pressure. Okay. Now, this pressure correction, when we are discussing this pressure correction, this pressure correction is corresponding to attractive intermolecular forces. This pressure correction is related to attractive, because V minus NB, this is related to repulsive, right? So when we are discussing this pressure correction is related to force of attraction. When we are writing that P plus N square A upon V square, this is the pressure correction. So in a container, if I am saying that this is a gas molecule which is going to collide with the wall of container, so the molecules behind them have force of attraction. They will try to attract this molecule, and because of that, the speed of this molecule, or the momentum, linear momentum of this molecule, is going to decrease. So rate of change of momentum transfer, the momentum transfer by this molecule to the wall of the container, will be less if it is attracted by the molecules behind. So that's why we are saying that the effect on linear momentum of a molecule will depend on the number of molecules per unit volume present in the container. More number of molecules will be there, more will be the effect on linear momentum. So one factor of N by V is due to effect on momentum transfer of one particle on wall. And we know that pressure is not because of one particle, pressure is because of all particles. All particles are participating in random motion, so all have the same probability to go and collide here, to transfer the momentum. So more the number of gas particles per unit volume will be there, more that factor or pressure will be on the wall of the container. That's why the second N by V is coming, because pressure is not because of one molecule, pressure is because of all molecules. So larger the number of moles per unit volume, larger will be the effect on the pressure correction, right? So this N by V is coming twice. First is for one molecule, and the second is pressure is not because of one molecule, pressure is because of all molecules. So N square upon V square factor will come, and this is proportionality constant A. This proportionality constant is related with force of attraction. So higher the value of A, more will be the force of attraction. So what we are saying that higher the value of A, more will be the force of attraction. For example, induced dipole force of interaction increases down the group in case of noble gases, because we have studied that in case of noble gases they are non-polar, so the van der Waals forces acting between them is London forces, dispersion forces, or induced dipole forces. And London forces depends on mass of gas particle, their surface area, their electrons, right? So as we are going down, all these factors are increasing. So van der Waals forces or London forces in case of noble gases increases down the group. So we can say that the force of the A proportionality constant related to force of attraction is minimum for helium, then it is neon, then argon, krypton, and xenon. Same way we can say for halogens, fluorine and chlorine is gas at room temperature. So the force of attraction between chlorine molecule is greater than that of fluorine molecule, because both molecules are non-polar. In non-polar molecules, we can say that London forces is directly proportional to the mass of the molecule. So we can say that mass of chlorine molecule is greater than fluorine molecule. So A for chlorine molecule is greater than A for fluorine molecule. So now we are discussing about van der Waals real gas equation. So when we want to write a real gas equation, we want to write the equation like an ideal gas. In case of an ideal gas, when we are writing PV is equal to nRT, where V is the volume of the gas, but the volume of the gas is free volume, because volume of gas molecule is negligible. So here it is representing free volume. This is free volume, because for an van der Waals real gas, we want to write an equation like ideal gas. So in ideal gas, volume is free volume. And in this van der Waals real gas, due to attractive forces, the pressure of real gas will be less. If we do some pressure correction, it is equal to the pressure of ideal gas. So this plus this, we can say that in pressure of real gas, if we do some pressure correction, then it is equal to the pressure of ideal gas. So now PV is equal to nRT. So for van der Waals real gas equation, this will be the equation. P real plus n square A upon V square V minus NB is equal to nRT. From here we can calculate that what is the pressure of real gas and how the pressure of real gas is going to vary. So we can say that pressure of real gas is equal to nRT V minus NB minus n square A upon V square. And from here we can find out that on changing the value of B, if we change the value of B, so on increasing the value of B, this is in denominator. If I increase the value of B, if I increase this value, this whole denominator is going to decrease, and if this whole denominator is going to decrease, this pressure is going to increase. So we are saying that on increasing B, P real is increasing, and that's why we are saying that B is related to force of repulsion, because if force of repulsion will be there, pressure will be more. So on increasing the value of B, force of repulsion will increase and pressure of real gas will be more. While when we are saying that when we are increasing the value of A, then pressure of real gas is going to decrease. On increasing the value of A, the pressure of real gas is going to decrease. So these are about A and B. B is related to size as well as force of repulsion. A is related to force of attraction. So the main point here is when we discuss about ideal gas, we are saying that pressure of ideal gas is equal to nRT by V. So pressure of ideal gas depends on number of moles, temperature, and volume. But for a real gas, apart from number of moles, temperature, and volume, it also depends on the value of A and B. Means it depends on the type of gas, real gas, the value of A and B for that real gas. So that is the difference between a real gas and ideal gas. Now compressibility factor, I have made a video of compressibility factor. There are 5 ways to represent compressibility factor. So we are not going in that detail. We're just introducing that. When we are talking about compressibility factor, we are comparing a volume of real gas with respect to volume of ideal gas under the same condition of number of moles, pressure, and temperature. So in place of volume of ideal gas, by using ideal gas equation, I can write an RT by P. And this can be written as Z as P into VR upon nRT, where P is pressure of real gas as well as ideal gas. N is the number of moles of real gas as well as ideal gas. T is the temperature of real gas as well as ideal gas. So for n is equal to 1, we are saying volume when in a container, when 1 mole of a gas is there, the volume of container is molar volume. So we can write Z is equal to PVm upon RT. Most of the time we are writing for 1 mole of a gas, where we are writing Z is equal to PVm upon RT. So application of compressibility factor on van der Waals real gas. Why we are studying upon gaseous state? Because gases are fuel. So when we are using these fuels in cooking cylinder, or when we are using these fuels for vehicles, or we are using this fuel in rockets, right? So we want to know what is the best condition to liquefy the gas. So that's why we are studying gaseous state. One main reason is fuel. So we have to liquefy the fuel. So we want to know that what are the conditions which is best for liquefying a gas. So that is the purpose, right? So when we are discussing under normal condition near about room temperature, most of time when we are discussing temperature is lying between 0 degrees Celsius to 25, near about 25 degrees Celsius. So near about room temperature, if we divide gases, there are two category of gases. So near about room temperature, in the first category of gases, there is sulfur dioxide gas, H2S gas, O2 gas, H2O gas, ammonia gas, carbon monoxide, carbon dioxide, and CH4 gas. So these gases have attractive forces under normal condition, or we can say that these gases, when we are discussing, since we know that there is a temperature known as Boyle's temperature, so near about room temperature, they are below their Boyle's temperature. When a gas is below their Boyle's temperature, then there is force of attraction between gas molecule. If there is force of attraction between gas molecule, it is easy to liquefy the gas. And there is another category, hydrogen and helium gas at room temperature. Room temperature is above their Boyle's temperature. If a gas is above its Boyle's temperature, there is repulsive forces. If there is repulsive forces, then we can say we cannot liquefy the gas. So that's why we have divided these gases in two categories. And here we are not discussing the effect of temperature. We are interested in effect of pressure, because all the time when we are discussing and nothing is mentioned about temperature, means temperature is near about room temperature. So the first case, at low pressure range. So when we are saying low pressure, when temperature is room temperature and we want to develop low pressure, so what is the way? We put the gas in a large container. So when we are putting the gas in a large container, now we know that there is a volume correction, that is V minus NB. So volume of container is large with respect to volume correction, so we can neglect volume correction. So these things are experimental. It's not theoretical that V minus NB. When we do the experiment near about room temperature, when we have to develop the low pressure, now most of the students should have that feeling that what is a low pressure for a real gas. Like for us, normal temperature is 180 atm. If temperature normal pressure is 180 atm. If pressure is greater than 180 atm, we'll say high pressure. If it is low, we'll say low pressure. But in case of real gas, it is not the situation. In case of real gas, when we are saying that pressure is high, it means 400 atm, 500 atm, 600 atm. If the pressure is 1 atm to 10 atm or 20 atm, it is low pressure range for a gas. For a gas, we should understand that from 1 atm to 20 atm, 10 atm, this is low pressure range. For high pressure range, it should be 400 atm, 500 atm, depending upon the gas, right? So it is large value of pressure, very large value of pressure. So when we are discussing here low pressure range, we are talking about 1 atm to 20 atm pressure range. In that pressure range, when we calculate that what is the value of volume, and we'll compare this volume with respect to the volume correction, then from experiment we'll get that this volume correction is negligible with respect to volume of gas. So by this experimental data, we are neglecting it. In ionic equilibrium, we discussed that there is a big number, there is a small number. If the big number is 20 times bigger than the smaller number, then we'll say that we can neglect the smaller number with respect to the bigger number. So here the situation is like that. So now if we neglect the volume correction, in van der Waals real gas equation, we can write that P plus N square A upon V square into V is equal to nRT. Putting the value of N is equal to 1, we can further simplify. P plus A upon V square into V is equal to RT. If we divide both sides by RT, left hand side will be PV upon RT, which is Z. plus A upon VRT. Right hand side is equal to 1, or we can say that Z is equal to 1 minus A upon VRT. So this is in low pressure range. This is the variation of Z with volume at constant temperature. When we are drawing this graph, we are not changing the temperature, and it is nothing is mentioned about temperature. It is near about room temperature 0 to 25 degrees Celsius, right? So Z is equal to 1 minus A upon VRT. From here, if we want to increase the pressure of the gas, we are keeping the temperature constant. In order to increase the pressure of the gas, what we'll do, we'll compress the gas. So we are decreasing the volume. If we decrease the volume over here, what will happen? Temperature is constant, R is universal gas constant, A is fixed for a gas. We are decreasing the volume. So from here, if we decrease the volume, the whole thing is going to increase, this thing is going to increase, and from there we'll get that the value of Z is going to decrease. So we can say that in low pressure, if we increase pressure at constant temperature, then volume is decreasing and Z will decrease. So what is the meaning of Z? Z, we are saying that volume of real gas upon volume of ideal gas, right? So if Z is less than 1, means volume of real gas is less with respect to volume of ideal gas, means there is force of attraction between gas molecules. So on compressing, when we are saying that in low pressure range, initially the volume of this container is large, and now we are compressing, that means when we are putting the molecules more nearer to each other, the force of attraction is going to increase. You can compare with this potential energy. Molecules are far apart. Now we are compressing. We are decreasing the separation distance. The force of attraction is going to increase. So if force of attraction is going to increase, it is easy to liquefy the gas. So that's why in low pressure range, we can liquefy most of the gases which is found near about room temperature, because in low pressure range, force of attraction is dominating. And if we compress, force of attraction will increase. If force of attraction will increase, it is easy to liquefy the gas. So that's why we are studying this variation of Z in low pressure range. Helps us to know that it is easy to liquefy the gas in low pressure range. The second point, in high pressure range, pressure correction is small. Again, this is not theoretical thing. From experiment, we know that there is some value of pressure. For real gas, this pressure will be 400, 500, depending upon the gas. This is a very high value, and now we compare this value with pressure correction N square A upon V square. We are comparing this value, and from experiment we are getting that this value is 20 times or more than this value. So we are taking this approximation, we are neglecting this value. So in high pressure range, when we neglect this value, we can write that P into V minus NB is equal to nRT. When N is equal to 1, we can further simplify. P into V minus B is equal to RT. If we divide left hand side and right hand side by RT, and further simplifying, we are getting that this PV and minus PB is equal to RT. If we take this minus PB on the right hand side, it will become plus PB. So dividing both sides by RT, left hand side is Z and right hand side is 1 plus PB upon RT. So in high pressure range, we are not talking in any pressure range. In high pressure range, from here we are discussing when the pressure is 400 atm onwards. So there is linear variation of Z and P at constant temperature. Again, here temperature is constant. We are discussing about isotherm. So on increasing pressure, Z is going to linearly vary. What is the meaning of this? In high pressure range, we already know that in high pressure range, the value of Z is greater than 1. Z is greater than 1 means there is repulsion between gas molecule. Now what we are trying to do, already there is high pressure, means the volume is already less. And now I am trying to compress this gas, and between gas molecules already repulsive forces are there. If repulsive forces are there, how much I will compress it, their repulsive forces are going to increase. So we cannot liquefy a gas in high pressure range. So this graph is telling that we should not liquefy the gas when repulsive forces are there in gas, and in high pressure range repulsive forces are there. So we should not liquefy the gas in high pressure range, right? So we have discussed about low pressure range, we have discussed about high pressure range. What about all the range of pressure? Moderate pressure range mein kya hoga? What we have to discuss that. Now if we consider all pressure range, how we'll write the value of Z? So this is van der Waals real gas equation, P plus N square A upon V square V minus NB is equal to nRT. When N is equal to 1, we can simplify it. P plus A upon V square V minus B is equal to RT. If I open the brackets, I can write left hand side PV plus A by V minus PV minus AB upon V square. So if I divide the left and right hand side by RT, this will become PV upon RT plus A upon VRT minus PV upon RT minus AB upon V square RT is equal to 1. From there we can say that Z is equal to 1 minus A upon VRT plus PB upon RT plus AB upon V square RT. So from here we can say that this minus sign indicates that this thing is related to, this contribution is because of attraction, and these two are positive things. So this we can say that this is because of repulsion. So there are both type of interactions, attraction and repulsion. So that's why when we are discussing in all pressure range from here to here, in low pressure range on increasing pressure, the value of Z is going to decrease. In high pressure range, it is linearly varying. So in intermediate pressure range, this is the exact graph. Or from this equation, we draw this graph. We are getting this graph. Now in this graph, there we have denoted 3 points, A point, B point, and C point. At point A, if we draw a tangent, the slope of tangent is negative, means variation of Z versus P on increasing pressure. On compressing the gas, the value of Z is decreasing, means force of attraction will increase. So we can say that if we are on the left hand side of B point, on increasing pressure, the force of attraction is increasing. This is important, right? When on the right hand side of B part, when we are at point C, the slope dz upon dp is positive. When dz upon dp is positive, means on increasing pressure Z is increasing, means force of repulsion will increase on increasing pressure. And at point B, slope is 0, slope of tangent is equal to 0, means on increasing pressure there is no effect on interactive forces. So they can ask a question that how this interactive forces are going to vary at different parts on this graph. So this is the actual graph, complete graph for variation of Z versus P for most of the gases near about room temperature. Now fourth point, for hydrogen and helium gas near about room temperature, we know that hydrogen gas is used as a fuel. In rockets, we are using hydrogen gas, but it is not easy to liquefy hydrogen gas. So here we are assuming room temperature. When we have to liquefy the gas, we have to decrease the temperature below its critical temperature, which is very low. So at room temperature, this gas has repulsive forces, right? So that's why this is known as permanent gas. So we are not discussing here temperature, we are discussing the effect of pressure. So for hydrogen and helium gas, the value of A is very small. Therefore, we can neglect pressure correction in all range of pressure near about room temperature. So what I want to say that here P plus N square A upon V square V minus NB is equal to nRT. So this value of pressure also depends on temperature. So when the temperature is near about room temperature, when the temperature, if you decrease the temperature, this pressure is going to decrease, because we know that temperature is related to kinetic energy. So if temperature is low, kinetic energy low, linear momentum will be low. So momentum transfer to the wall will be low, pressure will be low. So that's why we are saying that at room temperature, enough temperature is there so that this pressure is high. So now I am comparing N square A upon V square value at room temperature. This value is negligible in all ranges of pressure. This is negligible in all ranges of pressure. So I can neglect N square A upon V square with respect to pressure. So this is simplified to P V minus NB is equal to nRT. When N is equal to 1, I can write P V minus B is equal to RT. From there, I can write Z is equal to 1 plus PB upon RT. So when temperature is constant and it is near about room temperature, then for hydrogen and helium, it will linearly varying in all pressure range. So what is the difference? Before this also in high pressure range only it is linearly. Here in all pressure range it is going to vary linearly. Now this is the first graph and this is the second graph. If we compare Z is equal to 1 plus PB upon RT. PB upon RT. So we can find out what is the slope So slope is equal to B upon RT. So we can say that slope is directly proportional to B. And B is related to size, and the size of hydrogen molecule is greater than the size of helium atom. So the value of B is greater for hydrogen molecule than helium atom. So you should know that if these type of graph is there, they will ask that between hydrogen and helium, between first and second, which graph is for which gas. So we'll say that this is for hydrogen gas and this is for helium gas, right? So you should also know that the value of B means the size of hydrogen gas molecule is greater than the size of helium gas atom. So on increasing pressure, Z is increasing. Why hydrogen and helium is permanent? You can understand that hydrogen and helium, if you compress, already repulsive forces are there. If you further compress, repulsive forces are going to increase. So we can never liquefy hydrogen and helium at room temperature. That's why it is permanent gas. So what is the conclusion? Pressure is not only important thing, temperature is also important if we want to liquefy. If we want to liquefy, then temperature should low, and we should liquefy the gas in low pressure range. We should not liquefy the gas in high pressure range, because in high pressure range repulsion will be there. So low temperature and low pressure is useful to liquefy a gas. We should compress the gas in low pressure range and at low temperature. So the last point, for all type of gases at low pressure and high temperature. So this is the value of Z I have written without any approximation. We are saying that for a van der Waals real gas, the value of Z is going to vary like this. Z is equal to 1 plus Pb upon RT minus A upon VRT plus AB upon V square RT. And this question is very common in exam. So many times it is asked that under low pressure and high temperature condition, a real gas will behave like ideal gas. So this is a mathematical proof. If pressure is low in this thing, you can see that P is low and temperature is high, means this value is very small. So we can neglect this value with respect to 1. The second term, when pressure is low, volume is large. Volume is large, temperature is large, denominator is large, so this value will be small. So I can neglect this term also. And the third term, again, V square, volume, low pressure range, volume is large and temperature is, so I can also neglect this. So if I neglect second term, third term and fourth term, means Z is equal to 1. So Z is equal to 1 means PV is equal to nRT. So real gas will behave like ideal gas in low pressure and high temperature condition. Low pressure and high temperature condition, right? This question is very common in exam. Another point is there, I want to discuss here, sixth point. When we say there are two types of gases at room temperature, when we are drawing graph Z versus P graph at room temperature, most of the gases follow, here Z is equal to 1. Most of the gases follow this graph, but hydrogen and helium, the graph is like this. Now we are saying that if volume is very large, when volume is very large, means I am saying that pressure is tending towards 0. If you increase the volume is very large, pressure will be very low, means pressure is tending towards 0. So either if it is this type of gas or this type of gas, if pressure is tending towards 0, Z is tending towards 1. Z is 1 means a real gas will behave like ideal gas. So in a very large volume, means when the pressure is tending towards 0, a real gas will behave like ideal gas. Now, if you go through your NCERT, there are substances and their critical temperature is mentioned. And today we don't have time to derive this critical temperature for van der Waals real gas. So we are just discussing about the application of this critical temperature. Critical temperature is what? Critical temperature is the maximum temperature up to a gas, up to which a gas can be liquefied. So higher the value of critical temperature means the gas can be liquefied at higher temperature also. So for a liquefaction of gas, there are two factors which we should consider. One is thermal energy and the other is intermolecular attractive forces. So if the attractive forces dominate over thermal energy, then only the molecule can be liquefied. The gas molecule can be liquefied. So for liquefaction, intermolecular interaction should be more than thermal energy. So for a gas, if the gas is liquefying at higher temperature, means at higher temperature also those gas attractive forces are dominating over thermal energy, means the gas has tendency to form bond. So the gas can be easily liquefied. So here this table is given in NCERT, right? And a lot of questions being asked in surface chemistry also regarding critical temperature, because we know that ease of adsorption is directly proportional to critical temperature. That's why we are discussing these things given in NCERT. So you should know that among these gases, like if I have to compare about nitrogen, oxygen and hydrogen gas, they are diatomic, they are non-polar. So we can say that more molar mass, more will be intermolecular force of interaction, and more should be the critical temperature. So among hydrogen molecule, nitrogen molecule, oxygen molecule, it is easy to liquefy oxygen molecule, then nitrogen molecule, then hydrogen molecule. But here when we are discussing about carbon dioxide, water and ammonia, right? So in water there is hydrogen bonding and its critical temperature is largest among these. So we can say that water is easy to liquefy, means water vapor is easy to adsorb also. So this critical temperature here, by looking the data, we can say that the critical temperature of water is greater than ammonia, and ammonia is greater than CO2, and CO2 is greater than O2, then nitrogen, then hydrogen, and then least is helium. It is difficult to liquefy helium than hydrogen. So you should go through the data, right? They can ask question that among these 3 or 4 gases, which gas is easy to liquefy. Same way in your NCERT they have given some graph and they are discussing about boiling temperature. We know that what is boiling point. Boiling point is the temperature at which the vapor pressure of a liquid is equal to atmospheric pressure. So this graph is there between vapor pressure of the liquid and temperature graph is given, and this graph is given for 4 chemical species. One is water, other is ethanol, carbon tetrachloride and diethyl ether. So if you compare here, for diethyl ether the boiling temperature is least. For water, the boiling temperature is 373 Kelvin. For ethanol, the boiling temperature is less than that of water. For carbon tetrachloride, it is less than ethanol. So you should know, because these graphs are given in your NCERT book, you should know that what is the order of boiling temperature. If the boiling temperature is more, it means that intermolecular interactions will be more. Intermolecular interactions will be more means vapor pressure will be less. Less volatile liquid has high boiling point. So they can ask the order of volatility of the liquids or the order of boiling point of these liquids. So we should remember these things because it is given in NCERT. So most volatile is diethyl ether, then carbon tetrachloride, then ethanol, and then water. So these things are given in NCERT. That's why we are discussing it. Now these graphs are from NCERT. So here again we can say that these graphs are at 273 Kelvin, 0 degrees Celsius. Hydrogen and helium, we already know that B for hydrogen is greater than B for helium. So it's more easy to liquefy when we are discussing about these two gases, because here in low pressure range Z is less than 1. This is okay PV, but we know that Z is equal to PV upon RT. When temperature is constant, we can say that Z is directly proportional to PV. So here this variation is similar to that of Z. So being between carbon monoxide and CH4, which is more easy to liquefy, they can ask from there. So I will say that less value of PV means less value of Z. So in low pressure range, if Z is less, means force of attraction will be more. So we can say that CH4 is more easy to liquefy with respect to carbon monoxide. So you should know that it is easy to liquefy CH4 than carbon monoxide, means the critical temperature of CH4 is greater than critical temperature of carbon monoxide. If a gas has more critical temperature, means it can be liquefied at higher temperature. This is another graph given in NCERT. Very common questions are there. So in these two graphs, when we are discussing pressure versus volume graph, when volume is less, pressure is high. So in low volume means high pressure range. In high pressure range, if you compare here in high pressure range, for a real gas, when we are discussing high pressure range, when the molecules are nearby, repulsive forces will dominate. So the pressure of real gas will be greater than that of ideal gas. On the basis of that, we can say here that this graph is for real gas and this graph is for ideal gas. So in low pressure range means we have to see that in low pressure range, real gas molecules are nearby and repulsive forces will dominate due to repulsion, because in ideal gas, though there is no interactive forces, because of that, the pressure of real gas will be high than that of ideal gas in low volume or high pressure range, right? And same way, when we further increase and the volume is very large, these two graphs are going to meet again, because when the volume is very large, a real gas will behave like ideal gas. Or we can say here that here in low pressure range, if I have to compare, in low pressure range, molecules are far apart. So in case of real gas, force of attraction is there. If force of attraction is there, pressure of real gas is less than that of ideal gas. So these graphs are very common in exam. You can compare that. And this point is important. Critical temperature of CH4 is greater. It is easy to liquefy CH4 with respect to carbon monoxide. And next, this graph is also there where we are discussing this is for hydrogen gas. Then this region is low pressure region for nitrogen gas, right? So here we are talking about that this nitrogen gas is present its Boyle's temperature. Today we don't have time to discuss this Boyle's temperature, but we know that at Boyle's temperature, virile second coefficient is equal to 0. So in low pressure range, a real gas will behave like ideal gas. So this is for nitrogen gas. Oxygen gas has more van der Waals force of attraction because it has more molar mass. So it's below nitrogen than CH4 and this. So now here we have discussed that, okay, we can compare nitrogen and oxygen, but we cannot compare oxygen and CH4 here. So you should remember that among these, because these graphs are there in NCERT, critical temperatures they have mentioned in a table. So they can ask that between CO2, CH4 and O2, which gas is more easy? So from here you can find out that CO2 is more easy to liquefy, then CH4 is more easy to liquefy, then O2 is more easy to liquefy. So this is the order of critical temperature. Critical temperature of CO2 is greater than CH4, is greater than O2. So this is critical temperature of CO2 is greater than CH4 is greater than O2. And we know that ease of liquefaction is directly proportional to critical temperature, and ease of adsorption is also directly proportional to critical temperature. So here are some conclusions. Ease of liquefaction of water is greater than ammonia. Ammonia is greater than CO2. CO2 is greater than CH4, and CH4 is greater than CO. This order I am writing from the information given in NCERT. So you should know about that. This is very logical. We don't have to remember, all are diatomic. So more molar mass means more induced dipole force of attraction. So it's easy. So if a gas have high critical temperature, means the gas will liquefy fast on cooling. Force of attraction is necessary condition for liquefaction, but it is not the sufficient condition. So if force of attraction is there, why I'm saying that if Z is less than 1, it is not necessary that the gas will liquefy. When we study about van der Waals real gas, for liquefaction of the gas, the temperature should be equal to or less than critical. So the value of Z at critical point for van der Waals real gas is 3/8, which is very small with respect to 1. So if Z is less than 1 means force of attraction, but force of attraction should dominate thermal energy, then only the gas will liquefy, and that will dominate when the temperature is equal to or less than critical temperature. Gas cannot be liquefied above its critical temperature. So you all know this point. Critical temperature is the minimum temperature above which gas cannot be liquefied, or we can say that it is the maximum temperature up to which the gas can be liquefied. Below its critical temperature, this is also given in NCERT, below its critical temperature a gas is known as vapors, and water vapor critical temperature is 647 Kelvin, means it is equal to 347 डिग्री सेल्सियस. इसलिए हम रूम टेम्परेचर पे वाटर अगर वेपर स्टेट में हो, गैसियस स्टेट में, तो उसको वाटर वेपर बोलते हैं. नाइट्रोजन ऑक्सीजन को हम गैस बोलते हैं और वाटर को हम वाटर वेपर बोलते हैं, बिकॉज द टेम्परेचर is below its critical temperature. So if a gas is there and the gas is present below its critical temperature, then we'll say that it is vapor. There are many things to be discussed, like I have not discussed about liquefaction, I have not discussed virile equation due to limitation of time, but hope I have discussed many important points which is given in NCERT and which is very useful for you regarding your mains प्रिपरेशन. मैं आशा करता हूं कि आप लोगों को ये वीडियो पसंद आया होगा. अगर आपको पसंद आ रहा है तो प्लीज इसको लाइक करें, और अगर आपने सब्सक्राइब नहीं किया है तो इसको सब्सक्राइब करें. थैंक यू.